Dr. Dale Frail. He's from RAO, and he has his own Wikipedia page. And he's born in Canada, and he grew up in Europe. Then he spent most of his professional career in the United States. And he got his PhD from University of Toronto. And after finishing a GST postdoc fellow, he joined the research staff of NRAO. And he stepped down from the director of NRAO 2 years ago. And now he's mostly spent his time in research. And today he's going to talk to us about writing the pulsars.
Yeah. Yes, thank you. I thought I would start by, for those who don't know me, I actually began my research career in pulsars, and I've only just recently returned back to pulsars after about a 25-year break. Maybe you'll find this kind of funny, but the reason I got out of the field was that I'd written a paper with Alex Wilshon in 1992 on the discovery of the first extrasolar planetary system around pulsars, 1992. And I was horrified that my whole career was going to be defined by the first person to find extrasolar planets. And so I went off and worked on high energy transients. And so I feel like it's kind of safe to come back now and work in this area. But it's been great because I've been, through that I've managed to work with people like Ido Berger, and I'm actually here, was an external examiner for Kate's PhD examen yesterday. Oh, that's interesting. All right, so the work I'm going to talk to you about is really simple. It's just a simple idea that's an old idea that I dusted off from about 30 years ago when I'm applying with new techniques. And it began as a fairly small collaboration of about 4 of us here. A lot of power here. These 4 right here. And then it sort of mothballed over the last year into a larger collaboration. I'm going to begin by giving you some basic, sort of set the stage for what the basic search techniques are in pulsar astronomy, and then introduce a kind of a new idea, not a new, but dust off, I said, an old idea, and use that idea to search for pulsars, and show you a couple of interesting attempts that we've done with finding pulsars with Fermi unassociated sources, the GeV excess towards the galactic center, and talk to you about a curious excess in the galactic plane. So just to get you all on the same stage, there's pretty much only 2 basic techniques that are used for searching for pulsars. There's a blind search technique, where you stare at a piece of the sky, you collect time domain data, it's a function of time and frequency, and then you Fourier transform that and you look for periodicities. And there are these large-scale surveys of the entire sky looking for pulsars that way. And then the other technique, of course, is to go where the pulsars are, in this beautiful Chandra image here. There's a pulsar down in here. So you just stare at regions where you know there are pulsars. So you do a more targeted approach, gamma ray sources, SNRs, TeV sources. So you look in the areas where your thought they're in. So here you can tailor your search a little bit for the object, but here you're really globally applying the same search technique across a large region of the sky. So what I've been thinking about lately is, how do you hide a pulsar? The radio astronomy community has been incredibly successful at finding pulsars, find many, many exotic pulsars, but what are we missing? What is it about these fundamental search techniques that we might be missing? And so here's a couple of ideas on how we might hide a pulsar. One is just free absorption from a companion wind. So that gives you actually a nu squared kind of absorption. So that could hide a pulsar. And we know of these systems that have been found in optical and X-rays called redbacks and black widows that are completely obscured in the radio. Interstellar dispersion, although it can be dealt with, can be quite a significant factor in hiding pulsars. As I said, free absorption and other forms of absorption. Interstellar scattering is particularly bad. It's a nu to the 4th kind of, minus 4th kind of event, and I'll talk more about that. Maybe that missing, we've not yet found that black hole neutron star binary. Maybe it's in this hyper-elliptical orbit, at a highly eccentric orbit, and we're missed by standard acceleration searches. I don't know. And basically, I don't know what I'm missing. These are unknown unknowns. So I'm saying, can I apply a new technique that's different, complementary to existing techniques? And if history is any guide, what we can go back to is the discovery of the first millisecond pulsar, where prior to that point, the fastest pulsar was of order 33 milliseconds, and we made this quantum jump up to 1.5 milliseconds. And this is the story that's usually told about the discovery of the millisecond pulsar is the young Sri Kulkarni at the telescope, can't read the manual properly, and samples the sample function faster than he needs to, and does the Fourier transform, and finds this millisecond pulsar where nobody found. This is not the young Shriko-Carney, this is the old Shriko-Carney. To scale here. And later over a beer, you can ask me why my picture is in Shriko-Carney's office, but that's a separate story. Anyways, I won't go there. So it's a very great story, and you should learn about how Shri found the first millisecond pulsar, but the truth is actually more complicated. The truth was that he was pointing there because someone had done very careful work on measuring the spectrum of two objects in the field. One turned out to be flat spectrum, one turned out to be very steep spectrum. And it was the same way for the discovery of the first globular cluster pulsar. Radio astronomers, several of them, had established that there was a point source in this globular cluster that had steep spectrum spectral index. So the discovery of these really interesting objects was flagged by the fact that there was an object of very peculiar characteristics spectrally. And that's the essence of the technique I want to talk to you about today, which has sort of been largely forgotten, that you can go into the image plane and identify really interesting pulsars. And when you're in the image plane, of course, you're not seeing the pulsations. So this is a time average signal you're seeing. But the nice thing about this method is that if you can find steep spectrum objects, you're selecting without regard to their initial period, without regard to the dispersion measure, anything to do with scattering or orbital parameters. So if you can identify a steep spectrum source, you can find it, you can then follow it up by looking for pulsations in gamma rays or a radio. And so this is a picture from a survey that I'm about to talk about where that's the original millisecond pulsar. It just stood out like a sore thumb against the H2 region that it was next to. So my hope is not to, using this technique, is not to try to compete with the traditional searches. They're already very efficient. My hope is, and the word fracking is appropriate here, is to increase the yield of pulsar searches by using, say, a slightly orthogonal technique. Okay? And this has all been possible because of a survey that I worked on with a couple of grad students, postdocs I should say. The four of us had taken an existing survey that had been done at 150 megahertz, which is a very low frequency, I remind you. And the survey had been done in 2010, 2012 on the GMRT, but the data had been taken and the team run into some serious technical problems and weren't able to process the data sufficiently. I think they had released 10% of the catalog. So we went in with our own new algorithms for handling the ionosphere at these frequencies, and we grabbed this data from the archive. We processed all 5,000 pointings, and we put the catalog out there and made it available. Our 7 sigma catalog has 620,000 sources. Our 5 sigma catalog has nearly 1 million sources. This is the second largest survey ever done of the radio sky. And we made it available last year, publicly available on this website here. You can grab images, you can grab the FITS catalog, whatever you want. You can cruise through Aladdin if you want. But this is the highest resolution, most deepest radio survey done to date at low frequencies. It surpasses the LOFAR survey, LWA, by factors of 5 or 10 in some cases. And it's available for you today to do anything you want on low frequency astronomy. And I remind you, it's a factor of 10 lower in frequency than the traditional radio frequencies. The second thing that we've done, and again, this data is all public, is that we compared this TGSS low frequency survey with the centimeter survey, the famous NVSS, Jim Condon survey. So we grabbed we took our data, we convolved it to the resolution of the lower resolution of NVSS, and then we regridded them to the NVSS mosaic. So we just basically took the two surveys, put them on the same mosaic, and ran some modern source finding algorithms on both of them, and created a catalog. And now we can calculate the spectral index from 150 to 1.4 gigahertz, so over a factor of 10. So we created a catalog now of 1.4 million radio sources, 80% of the sky, with spectral index or spectral index limits on them. So it's a very valuable resource if you're a high-energy astronomer interested in the radio properties of sources. It's just available, again, the FITS images, the images, the catalog, everything is all available. All right? So that's and there's some beautiful figures in here where you can take all 1.4 million sources and have some fun with them, and I don't have time to talk about that. But those are the two fundamental databases I'm going to use to find pulsars. And to recap, the method is dead simple. You basically use two criteria. You measure the spectral index of the object, and then you have some measure of compactness. So this is the total brightness, the millijanskis per beam versus this is the total flux density in millijanskis, and then this is some measure of the peak intensity, millijanskis per beam we call it, okay? But it's a specific intensity. So a diffuse source will have a large ratio here. Point sources will have a ratio of order unity modulo signal to noise, okay? So there are sources here. So here are all the known pulsars with their spectral index and their flux ratio. And there's a few that are high here. Some have pulsar wind nebula hiding underneath them. Some scintillate and break the Van Zedek-Zernike theorem. But most of them, as you can see, have, well, I have put it right here. 0.3% of all radio sources have spectra steeper than minus 1.5. So the radio sources here in the sky. But pulsars are 75% of them have these steep spectral index. So if you can carve off this piece of space this way, looking for compact steep spectrum sources, you're in an interesting part of phase space for looking for pulsars. Okay? And so this is like shooting, what do they call it? Shooting something in a barrel? Fish in a barrel. Okay, so here's an NVSS image at 1.4 gigahertz. And imagine the spectral index is minus 2. The object is 100 times brighter at 150 megahertz, right? It just jumps out of the page at you. It's not detectable in NVSS. It's like sub-millijansky probably. And just jumps out at a few hundred millijanskys here at 150. Likewise, in the southern version of NVSS, there's a very faint maybe source right there. But here it's like 250 millijanskys, which is, you know, kind of thing you can detect with Radio Shack kind of technology. All right, so easy. First thing we did is we looked at the Fermi-associated sources. We looked at all of them. We don't have to focus on some small select of them. We don't have any bias at all. We just said, show me the 1,000 Fermi sources that are above this certain declination range. So we looked at the 3 FGL, and we found 11 pulsar candidates there. And then we used, for experts, we used the 7-year catalog. So we didn't have the 8-year catalog that time. So we identified a further 12 candidates there. And since the resolution of the surveys, NVSS and TGSS, was of order 25 arc seconds, we did some follow-up to eliminate false positives. Our largest source of false positives are high redshift radio galaxies at a redshift 4, redshift 6. There's one at redshift 6. It's nice. That's our false signal. Those really cool radio galaxies at a redshift of 6. Okay, but nonetheless, we were able to eliminate them because they are typically extended on a scale of about 5 arc seconds. The pulsars remain compact. And so at the end of that analysis, so here's some of the VLA follow-up and the ATCA follow-up. These are rejects, okay? These are probably redshift 4 AGN boring stuff. Sorry. So we ended up with some false positives. We have 6 pulsar candidates, 3 FGL. We had 10 more in the 7-year catalog. And some of them actually are extremely well studied, have been known about for years. And this one here, I don't remember its telephone number, but this one had data from 5 separate surveys and showing its minus 1.7 or minus 1.8 spectral index all the way. So the first thing that we're able to do is I'm able to provide my gamma ray colleagues a position that's accurate to about 1/10 of an arc second. Okay? So they don't have to search over a region now with the Einstein at home effort. They don't have to search over these regions that are several 6 or 10 arc minutes in extent. I can tell them exactly there's a steep spectrum source at that location. Go search. And they did, and we found 2 immediate pulsars at gamma ray energies, 2.2 milliseconds, 2.8 milliseconds, all based on the steep spectrum and based on that position that I gave them. This work is still unpublished. And here's kind of the current state of the art of where we are with this effort, and I want to go through a few other things, so I'm moving a little fast. But here's kind of our report card. Here are those candidates I referred to, the 10, and these are the 6 candidates here, and these are the 10 other candidates. And we've detected 1, 2, 3, 4, 5, 6, 7 pulsars in this group. For the gamma ray people, they know exactly what this nomenclature is, but that's a gamma ray pulsar that's millisecond, gamma ray radio millisecond, binary radio millisecond pulsar, and then I put the periods next to them. So just to highlight, I'm not going to talk in detail about the pulsars because this is a technique talk. But this one here is I think the 2nd or 3rd fastest pulsar known now, it's a binary, and it's in like a 1.5 hour period, and it's already been incorporated into the pulsar timing array. Now, this is the cool part. That's fine. Okay. The cool part is this is the gamma ray grade that they would assign to this. So when you go and you do pulsar searches, you don't look at the whole 3 FGL catalog. You look at pulsar-like spectra, pulsar-like light curves in gamma rays, and then you rank them by A, B, C, and then unlikely to be a pulsar. Well, the ones that we pulled out with using this image-based technique, you can see this was unlikely to be a pulsar. This was third level class of a pulsar. This is thought to have been unlikely a pulsar, pulsar C, pulsar C, pulsar C. So they would have been in the bottom of a rank ordered list. They would not have been the first things to look at. And yet, They pop out with this image-based technique. So at some level, I've already satisfied my criteria of looking for hidden biases. Right? Here's not being very imaginative. The next thing we did is say, okay, gamma rays, unassociated sources. Let's go look at the galactic center. You know, I probably insult the audience by trying to explain what the gamma ray excess is, but you all know fairly well here that there is an excess of gamma rays at the galactic center once you remove the diffuse model. There's a component that's about 2.5 arc second, 2.5 degrees, I should say, and then there's some extended emission that goes out to, I think, 10 or 12 degrees. And there's a debate about what this is. The physicists think this is annihilation radiation, and they're going to win some Nobel Prize free tickets to Sweden. The astronomers, are being a little more practical, have argued, based on the spatial properties and the spectral properties, that this is likely a young pulsar population, or more likely a millisecond pulsar population. And there's a paper by Chuck Haley that came out last week that I haven't had a chance to read that addresses some of this issue. But it turns out that there are surprisingly few pulsars, radio pulsars, in the bulge and in the galactic center. Not just around Sagittarius star, but in the broader region. This is a radio image of a 2-degree region with a 2-mass set on top of it. And the problem with this has always been that this is a very turbulent region. The galactic center, as you can see almost visually, has got a lot of ionized gas, a lot of non-thermal gas, a lot of explosions. And that turbulence, as you propagate the pulsar signal between us and the galactic center, from the galactic center between us and that, is a lot of turbulent gas, and that creates temporal broadening. And that temporal broadening basically stretches out the signal until it's a DC signal, and you can't see it in the Fourier domain. But you can see it in the image plane domain. So I asked my summer student, I said, well, go take a look at the TGSS data and find some steep spectrum sources within that region I just showed you, within that pretty picture I just showed you. And he found 2 interesting candidates that were steep spectrum. This is one of them. And then we followed up with a VLA image, because that's the original resolution of the thing, and we found a minus 2.55 source. And right next to it is some reasonable looking flat spectrum source. So then we did a follow-up search at higher frequencies where the scattering is reduced by nu to the 4th power. So traditional searches are done at 1.4 gigahertz, but if you shift over down to, you don't know what S and C band are, I realize I forgot to change that. So that's at 2 gigahertz and 5 gigahertz typically. So the scattering is much reduced, and lo and behold, we found a pulsar. A millisecond pulsar, again, 2.2. I'm finding a lot of 2.2 millisecond pulsars. I don't know why. It turns out that it's not in the bulge. It's about halfway along the line of sight, so it's a foreground object, but it was a great demonstration that this technique can actually work. To go into the image plane, identify steep spectrum sources, and you will find interesting pulsars. So we've continued this work, and this is not really finished yet. We're actively working on this week. We've done 2 different things. One is that we've taken that same 2.5 degree region, 2.5 by 2.5 degrees, and we've gone much deeper looking for steep spectrum sources. And then we've also looked at the pulsar, the Fermi group, the Fermi collaboration has published a large collection of Fermi sources within the bulge region, and we focused on 17 of them that are pulsar-like. And I think we've got something on the order of a dozen candidates that we're still looking at now. And so we're going to follow this up with looking at higher radio frequencies to see if we can see them. The idea would be they've been missed in the past because they're scatter broadened, and they're in this little piece of phase space in here that we're still working on. And then the other again, I can actually, since I know the position, I can tell my Fermi colleagues, go here, search, fold the data, and see if you can find the pulsars. All right, so that's a progress report on that. All right, so the third and interesting result I wanted to report comes out of that spectral index catalog that we produced of the 1.4 million sources between NVSS and TGSS. And there's just something very curious going on here, which is you can take those 1.4 million sources and plot them any way you want. You can plot them, but I'm plotting them here as a function of galactic latitude. So follow the black line, okay? The dip in here, so this is all the sources, no matter what their spectral index is like this, all right, as a function of galactic latitude. And you can understand why it falls off here, because there's a cutoff in the deck. So at some point there are no sources with a declination of minus 80, because the cutoff is about minus 40 degrees declination. All right, so there's if I did the whole sky, this would be a symmetric function, but it's not. Anyway, so you're missing the most southern part of the sky. And then it dips in here because the galactic plane actually increases the noise so much that your number of sources drops in the right in the area of the galactic plane. But nonetheless, it's a reasonable distribution. And then if you plot, say, flat spectrum sources, the green ones, meaning just one end of the Gaussian, it also follows the distribution, the general distribution with its bumps and wiggles and stuff. But if you say, I'm only going to plot steep spectrum sources, you end up with this weird red bump here at plus or minus 10 degrees. There appears to be some kind of excess, and normalize and subtract off. It's on the order of 100 sources or so at low latitudes. There's a lot of steep spectrum sources, but they're not, as far as I know, they're not known. Well, no, we've taken out the known pulsars. But there is also this curious excess of objects in the plane. Steep spectrum, not previously seen to be known as pulsars. And the challenge for this is really quite interesting. What can they be? Because the state-of-the-art surveys of the galactic plane that are going on right now are highlighted here. Typically, the brightness of these things is on the order of 1 millijansky. So they were, for over a range of large periods, they could actually have been easily detected by the current state-of-the-art radio surveys that are doing blind surveys of the galactic plane. But they've missed them somehow. Okay? And we've looked at the systematics of our sample to see if there's errors that are causing problems. And there's a 10-minute digression. I can talk about that. But we think we understand our errors well enough that this is not a sample that's actually dominated by errors. That the steep spectrum compact sources are genuine sources. And so maybe some of them are really, really steep spectrum at gigahertz frequencies, and so they just disappear off the search radar of these experiments. Some could be too fast. You can see here the sensitivity of these experiments is a function of dispersion measure, which is a rough measure of distance. So you could imagine, let's say, a 2 millisecond pulsar at, what would this be, like 4 kiloparsecs or so in a typical direction. Yeah, so it would get out of the sensitivity of something like this experiment here. So unless it was quite bright. So nonetheless, so you can imagine a couple of these scenarios, eccentric binaries for a few of them, but you can't explain 85 or 100 of these things this way. You just can't. So I've got an idea of what it might be, and I'm just happy to talk to people who are experts on this. But you can take the known pulsars and plot their scattering properties. So this is the temporal broadening of the pulse profile as a function of dispersion measure, which I've told you is as you know, is probably the ionized gas content. It's a column density. And so it's a rough measure of distance. And it tracks really well at low dispersion measures, meaning when the line of sight isn't very large, then there's a fairly linear relationship between the scattering and the amount of gas along the line of sight. But then as you get further and further out, the chance of hitting clumps of gas get higher. And so you can see the dispersion here goes up by, the amount of scattering can be anywhere between 10 milliseconds and 1,000 milliseconds up in here in some of these things. So at higher dispersion measures, it can be quite high. So what I think might be happening, and I don't know, is that this is some kind of population of objects that have been missed by the traditional searches because they are normal pulsars, meaning 100 milliseconds or something like that, but they have higher than average scattering measures, and so they've been hidden. And so one way to demonstrate that would be to go look at higher frequencies at a sample of these things, which we haven't done yet. I have 2 more slides, and then I'm finished. So just, again, I told you I'm going to give you an idea talk, and this is basically a simple old idea that's 30 years old that Shri used to find the first millisecond pulsar. And it's free of all the usual biases. And so our hope has been, and we're still working on it, is that we're going to use this technique to find really exotic pulsars missed by traditional techniques. We focus on the galactic center and the bulge because we want to see those objects. We're hoping to find something truly exotic among the Fermi unassociated sources. And I pointed out this steep spectrum excess, which I have no idea what it is right now, so that's an interesting area. And I have several ideas about how to proceed in here, but just one slide to show you where I think we should go with this in the galactic center. This is a paper by Color et al. It's a very nice paper. I'd urge you to read it if you're interested in the bulge pulsar population. And they go through, do an analysis and show that they think they need of order 300 bright millisecond pulsars at the galactic center in the bulge region And they say, well, okay, let's assume that's what we need to form the gamma ray excess. So that's on the order that they need. That's a rough number. And they need 2,250 hours with GBT time to just kiss the top of this distribution. So here's GBT. So they think they can find 34 bulge pulsars with 2,250 hours. Not a great yield. Okay, it's a lot of telescope time. So what I'm advocating, it's just sort of a back of the envelope application, is you start with the imaging technique. You can image. This is at 90 centimeters, so you get something on the order of 4 square degrees in that image. So you can image large chunks of the galactic plane that way. Now you're at a frequency where the pulsars are arguably between here and here about a factor of, well, I've already calculated, about 10 or 20 times brighter. So you can identify in the image plane the steep spectrum sources that are likely candidate pulsars, and then you target them. Instead of surveying the whole area with a single dish, then you target them at frequencies like 5 gigahertz or 3 gigahertz to get past the temporal broadening. And again, back of the envelope calculation suggests that we could find of order 150 of these things with about 1/5 the total telescope time. So it's worth considering that you could dig deeper into this distribution and you could find more of these pulsars. And then since I'm here, I wanted to end with a poem because I've been talking about biases. This is a poem that I've had in my PhD thesis, has guided me my whole career, which is the idea that this is Henry Wadsworth Longfellow, which is who lived here. It's a beautiful poem about how the world looks like when you look at the world through a different light, and it's a constant reminder for me to always, when there's a technique out there that's finding something, always look orthogonally, always look in a little bit direction. So the last 2 lines are the ones that I always remind myself. We see, but what we have the gift of seeing, what we bring, we find. We bring our biases to problems. We should also be aware that we're only going to find the things we look for when we bring a certain technique. And we should use these techniques to find more pulsars. Anyway, sorry for the poetry, but it fits, I think. So. Yeah, so what I did is I took the colloidal numbers, and if in the best possible case, I would detect of order half of that population. Not just in the inner 2.5, but I'd have to go out. Remember, the Fermi excess goes out to about plus or minus 10 degrees. So I'd have to search. I would have to search about 100 square degrees. I think I have to go through the calculations again, but it's something on that order. 100 square degrees, and the best optimistic scenarios would be that I would find about half that population, if it's there.
So, some of us are very interested, including Jason, who just asked that question, in using X-ray pulsars as an X-ray navigation.
Yep.
Method. And so have you checked the X-ray fluxes of these new
A few I have, yes. Yeah. And so far I haven't found any X-ray emission from any of these ones yet.
Oh.
No.
We need a program with Chandra.
But they're mostly just swift pointings with like 3 kiloseconds. Yeah, so there isn't a lot of good data on them. Yeah. Sorry.
Dale, have you thought more about the black hole neutron star binary problem, which you mentioned briefly, and using your soft source technique to find the candidates, but then extending acceleration searches to extreme values to look for highly eccentric systems? Have you tried that?
So the basic idea is that if I found a candidate, would be a good place to start. So the idea is to develop some candidates that are really robust candidates that fail the traditional search. So if I come up with a short list of really interesting candidates, remember, in the galactic plane, there are no minus 2.5 sources that are not pulsars. So I come up with a short list of very interesting candidates, and then I tell my colleagues, do a deeper acceleration search, do a harder acceleration search, because this is an interesting candidate. And I think if it turns out to be an X-ray source or a Fermi source and a steep spectrum radio source with polarization, then my colleagues will do that extra effort of searching, the full parameter space of acceleration search. The other area that would love to talk to people about is what is the current thinking about the eccentricities of black hole neutron star binaries in light of LIGO and other work that's being done in this area. Because we were supposed to have found them a decade ago. We've found of order 2,500 pulsars right now, and they should have, my memory is they should have been found around the 500 mark in terms of their frequency, and they haven't been found yet. So, yeah, you had a question?
So from the literature that I remember that for the Galactic Center documented annihilation signal, if there were some studies that if they use already known young pulsars, they can actually reproduce that excess to Fermi seeds. So now you're discovering new sources. What would happen then if you add those pulsars in the signal and then hold that to the Fermi response?
Yeah.
Would you get excess over excess?
No, so you're saying the existing population can explain
Yes.
it? I'm not aware of that.
I've seen a few papers actually.
I mean, yeah, sorry, but one of the problems with the young population is you have to continually replenish that population. So the advantage of the millisecond pulsar population is they exist for a longer time with higher E dot. So I would love to hear about, if I'm wrong, I'd like to hear that reference, because I'm obviously don't know the full literature on the Galactic Center excess, but you're saying that people think they've accounted for the population.
Right, there were a few papers actually saying that they have already found these pulsars and they can explain galactic synthesis.
No, but I don't think they've seen pulsations. I think they're basically using X-ray and gamma ray emission to say these sources could account for them. But what I want is to detect the period and the E dot. I think that's the route to, they've got the integral. I want to get the derivative. I want to see what the actual values are. I think, but I'd be happy if you could email me that paper. Yeah. Yes.
Are you going to find the fast guy?
I'm not. Actually, that was a facetious answer, but the number of, so in the Fermi sources, though, we're doing two things right now. One is we're looking at the Fermi sources of the Galactic Center. Those are sufficient, they have sufficiently rare number of sources in those Fermi things that I don't think my colleagues would mind if I gave them 3 positions to search with sub-arc second position accuracy. So they're probably going to search for a sufficiently bright gamma ray source. I don't think they'll mind searching for 3. So that's one answer to your question. But in general, no. That's going to be my bias. Everyone has a bias, right? Yeah. All right.
We are very fortunate to have Joe Mohr from LMU in Munich to give us part of this high energy colloquium talk. And so Joe Mohr is a professor at LMU, and he actually had his graduate degree from Harvard. He worked with Margaret Geller for his dissertation project. Then he went to University of Michigan to work with Gus Everard, and he took one of the earlier Chandra fellowships to go to University of Chicago to work with John Costrom. And he's actually one of the founding fathers of Dark Energy Survey and South Pole Telescope. So we are very happy that you're here.
Thanks a lot, Ezra. Okay, so yeah, I'm going to give you some insights into cluster structure as seen through scaling relations. In particular, the new part of this, I think, is this sample of clusters that extends to high redshift. So we can do homogeneous mass estimation, stellar mass, ICM mass, halo mass, over a broad range of redshift and mass. And this is really the lead of this work is Yinan Cho, who's now at Academia Sinica in Taipei. And of course, we've had many contributions from SPT in particular and also DES. So why might you want to study scaling relations? You can learn things about how galaxy clusters form. Hopefully one of the conclusions today will be interesting in that regard. The scatter is telling you something about the variation at fixed temperature, fixed mass, something like that in structure of the galaxy clusters. The overall, I guess, slope in this case typically is sensitive to feedback from AGN or star formation. And ultimately then, measurements of the stellar mass fraction, the ICM mass fraction, can be compared to simulated clusters containing feedback, and we can understand if we can match the simulations to the observations, we can then use those same simulations to understand how the feedback is affecting the matter power spectrum, which is crucial for future cosmic shear experiments, among other reasons. So we really want to have a simple selection, broad redshift range, and mass range, and accurate masses. And we think we have that with SPT. Oh, sorry. This is basically the impact from a recent paper by Volker Springel of baryonic physics, you could say, on the matter power spectrum. Ultimately, we should be able to help determine which of these models is an appropriate description of the real universe. So I'm going to say a little bit about the halo mass estimates, the South Pole Telescope selected clusters, because that's crucial here. Review how you estimate stellar and ICM mass measurements, go very quickly there, and then try to present the results. And you can look in this paper for more details. Wanted to show this. I know you guys know about the Sunyaev-Zel'dovich effect, but this nice picture from Leon van Spraebroek is nice. I mean, one of the showing low energy CMB photon coming in and being scattered by a high energy electron in a cluster. We're seeing that absence of photons, or that shadow. You can see the clusters show up as sort of shadows here in this simulated CMB sky. This kind of project that I'm talking about today, which brings together SZ and X-ray, was certainly something that motivated Leon. Right, you've seen probably the SPT sample. I just want to say here, remind you that it's been, the sample I'm using is from the so-called SPT-SZ survey, 2,500 square degrees. There's a little green patch up there next to the telescope. 500 clusters plotted here as black points in mass versus redshift. There, it extends to high redshift as we expected and hoped with SC selected samples. There are about 30 systems above redshift 1. The maximum redshift is somewhere out here, 1.75. Paper on that should be coming out very soon. And basically 91 of these systems have been observed with Chandra through a variety of proposals, including X-ray visionary proposal that Brad Benson and Alexei Viklenin and others were successful in bringing down. Okay, and this is basically then the plot of mass versus redshift of the sample that I'm going to show you. So we can do cosmology with the SPT selected clusters. That was our primary goal. There are a variety of plots here from our latest analysis, DeHaan et al., 2016. The important thing for this talk is that in the process of doing this cosmology, you need to be able to connect the SC observable, which we call XI, or the signal to noise, to the underlying mass. And we need to have some kind of observable mass relation. We have to calibrate that empirically. That means, that implies, that if we can do cosmology, we can also use those halo masses to then study the individual clusters. And that's, of course, what we're doing here. Whoops. No, there we go. So a few more words about the observable mass relation. Don't have much time to spend on this. But basically, we create some kind of power law relation between the signal to noise. You can see there's a mass trend. There's a redshift dependent trend. And in addition, there's some intrinsic scatter at fixed, intrinsic scatter in the observable at fixed mass. So a nice thing about this observable mass relation is we calibrate it empirically. It's consistent with the data. You can see here's just an early subset of the data where we plot YSE versus M500, and you can see that there's at least there's a reasonably nice relation. When we calibrate this empirically, we get best fit parameters, but we also get a range of parameters that are consistent with the data. And so that means when it comes down to studying either cosmology or the scaling relations, like I'm going to show you today, we can marginalize over these uncertainties and effectively include the systematic uncertainties in our analysis. Okay, so that's nice. In this empirical analysis, empirical calibration, we're constantly trying to improve that through weak lensing, galaxy kinematics, external priors even, although less so now. And what I'm going to show you is sort of state-of-the-art given the data that we have available now. It will get better over time. Characteristic SC-based mass scatter is something like 15 to 20%, including the systematics added in quadrature, something like 25% per cluster. So this is helpful to us because we can, sorry for that, I'll try to be. That's helpful for us because we can estimate masses relatively accurately on a single cluster basis, which typically we couldn't do with just the weak lensing data on that cluster alone. Okay, how do we, sorry. I think I've pretty much said most of this. The one thing that I wanted to, there's some numbers here which won't mean too much, but it just shows the various parameters, parameter uncertainties that are used in this analysis. Again, emphasizing single cluster mass estimate at sort of 25% level, including systematic uncertainties. I'd like to also mention two other things. There have been cross-checks of this analysis, this mass calibration analysis that I'm talking about from weak lensing, and we basically find no evidence for problems in a sample of 32 clusters and dynamical mass estimates in a sample of 110 clusters, and I show sort of the mean offsets in mass. Good. The other thing is covariance between the SC observable and the X-ray ICM is the particular thing that we're interested in today. And I can just say in this analysis we ignore that. We can ignore it because in these two previous publications we've looked for that covariance and we haven't proven that it's not there, but we know that it's weak enough that we can't detect it in a sample of about 90 clusters. Okay? Good. And the remaining wiggle room in the mass scale of the SPT clusters then is included as a systematic uncertainty in these baryon scaling relations. Important detail. Now, measurements of stellar and ICM masses. You've seen this, just a quick review. So we're basically doing SED fitting to each galaxy, towards a galaxy cluster, towards each of the SPT clusters that I showed you. Typically, we have 4 optical flux measurements, a couple of infrared measurements from either Spitzer or from WISE, and works pretty well for estimating both the photoz's and the stellar masses of the galaxies through established techniques. What we actually do is we measure the stellar masses of all these galaxies. We look at the profile in the stellar mass projected. Well, actually, we deproject it, so we have the profile of stellar mass as a function of radius. And then using the halo mass from the SC that we've just talked about, we can get the R200, the sort of virial radius of the cluster, and we can simply read off what the stellar mass is at that radius. For ICM masses, you know that they come from X-ray surface brightness profiles, X-ray temperatures, from Chandra, XMM typically. In this case, all from Chandra. So we can solve for the ICM density as a function of radius. We can integrate that to give us the ICM mass within a radius. And then again, with the halo mass information, we can calculate the R200 and pull out the mass. So that's basically what we do. Here is a set, if you go to the paper, if you go to the paper, you'll find a set of measurements for these 91 clusters, which might be useful for other studies. ICM masses, stellar masses, cold fractions, we'll say more about that in a bit, and the halo masses. Okay, good. So finally then, the results. The scaling relations, oh sorry, one more preliminary. So we're fitting these power law scaling relations. Here's a characteristic form where the X-ray observable is equal to some normalization parameter A times some mass to the B power times some redshift function to the C power. And in each case we use measurement uncertainties, of course, correcting, including that information directly. And then we solve for some intrinsic scatter in each of these different scaling relations. And you can see that the mass and the redshift trends are defined with respect to a pivot mass and a pivot redshift to try to break the correlated errors in the slope and the normalization, or the trends in the normalization. And so we're basically looking at something like 5 10 to the 14 solar masses. Our sample goes from, these are actually M500s, not M200s, are going from something like 3 10 to the 14 up to a couple 10 to the 15. And our pivot redshift is 0.6, and our redshifts are going from 0.2 to 1.25, something like that. Here's some other details. We're fixing cosmology, and we're including the scaling relation, the halo mass uncertainties in the way that I've already described. Okay, then maybe some results. What did we find? So we know that clusters are growing through the accretion of low mass clusters, of subclusters and groups, and presumably also material falling in from around the clusters. Although we like to think in hierarchical structure formation context that of these massive systems being composed of the low mass systems. But you can see immediately that there are some issues with that. Here we have what we actually fit was the stellar mass versus the halo mass, so this. But then of course we can turn that into a stellar mass fraction, which is easier to discuss. And you can see that for low mass systems down here around 10 to the 14, which we're not probing, but we show not only our data here in black points, but other data sets as listed above, that the groups on scales of 10 to the 14 have much higher stellar mass fractions than the clusters on scales of 10 to the 15. So this has been known for a while, since 2003 at least. And so it's already becomes clear that you can't build a low stellar mass fraction object out of components that all have high stellar mass fractions. So what's going on? It was suggested that maybe in the process of merging, the galaxies are losing quite a bit of their stars, and so that we would expect to see an intracluster light. This was suggested back in 2004 by a student of mine. And unfortunately, people looked at clusters and didn't find the right amount of intracluster light to explain that. Could there be halo mass errors? Well, we're doing this experiment because we feel we understand our halo masses quite well in the SZ sample. Shoot. Could it be M-star errors? We don't think so. Could it be redshift trends? People were saying, well, the high mass systems that we observed in the low redshift universe, back when we first looked at this in 2003, 2004, aren't built of the groups in the present epoch universe, but they're built from groups at an earlier time. And so with this data set, we can then look at the redshift trends, and you can basically see here F star versus redshift at some F star at some characteristic mass or pivot mass as a function of redshift. And you can see that there basically isn't much in the way of a trend. What is shown here is a trend in F star on average in the universe using Planck for the Baryon fraction and using Musin 13 to measure the stellar mass fraction averaged in the field. And so you can see over time there's quite a bit of evolution in the overall field stellar mass fraction, but in clusters there's no evidence for variations, let's put it that way. They could be there. You can see the uncertainties are still significant, but there's certainly no suggestion of any trend. Okay, in ICM Mass we have a kind of similar but inverted story. On average, in this case, groups, low mass systems, have lower stellar mass fractions than high mass systems or clusters. This, at least the first study that I'm aware of that showed that groups have low ICM mass fractions, was by Larry David in 1993, studying some of the early observations from Rosette. And then later, at the end of that decade, we put together a big sample of systems and showed statistically that there is a big difference, a trend. So we see that now in this more recent sample. This again is a compilation of our points in black and other previously published results. So we see that, again, there's an issue that you can't build massive systems out of the low mass systems because although there's quite a bit of scatter, on average, the groups have a lower gas fraction than clusters. And here again, we show the universal value as that yellow trend. So what could explain this? back in the 20 years ago when people were first discovering this and talking about it, people really felt that AGN feedback was a nice explanation for sort of puffing up the gas in low mass halos, and it would have a differential effect where a certain amount of feedback would have a greater impact on groups than on massive clusters, and therefore you'd introduce this trend. That is certainly one possible explanation. But it's interesting here also to look at the redshift trends, and we really don't see any change in the ICM mass fraction at fixed mass as a function of redshift. There's a little, there maybe is a little bit of a trend there. I'll show you, you can look at the points in the paper, you can look at the actual parameters and parameter uncertainties in the paper, but there's no statistically significant evidence for a trend here. Okay, what about the baryon fraction? Well, the baryon fraction basically looks like the ICM mass fraction because it's dominant. The ICM dominates the baryon fraction. And so we see a strong mass trend there. A weak, maybe I messed this up. We also see basically no evidence of a strong redshift trend. And then cold fraction. What is cold fraction? Cold fraction is the fraction of baryons that have been turned into stars. Again, all these stars implied in our approach are only the stars in the galaxies, so we're not able to study the intercluster light with the DES data that we're using. Anyway, the cold fraction then is the fraction of baryons that were turned into galactic stars. And you can see that this also changes as a function of matter, as a function of halo mass. So for whatever reason, low mass groups and low mass clusters and groups have roughly three times higher success rate in turning a given mass of baryons of intercluster medium into stars. So you can see it basically falls from about 15% cold fraction at 10 to the 14 to 5% at 10 to the 15. And here also we really don't see any redshift trends. Okay, so what have we... Oh, and here are... Sorry. I think I had that a little out of order. Here are basically the results which you can look at in the paper if you're interested in what we find when we combine these data sets and measure mass and redshift trends. What have we learned, or what are the implications of this? So the surprising result, or the interesting result that we were able to use to extract from the SPT data set as observed by Chandra and DES is that there are very weak redshift trends. Okay, so what does that mean? So the stellar and ICM mass fractions in clusters, in cluster virial regions, are differing systematically from the cosmic average values. So in each of those plots, you can sort of see how the cosmic values are changing. In some cases, they don't change, and how they compare as a function of mass and redshift to the clusters. Characteristically, they're different. And in the infall regions that live between the virial regions and the field, they must have sort of intermediate values. So I think what we're seeing can be interpreted roughly as saying that clusters are growing then not only through the accretion of the subclusters, but also through the accretion of any sort of low-density material in the infall regions that are surrounding the cluster itself. It could be direct infall from the infall regions of galaxies and the gas associated with them. It could be the infall regions of subclusters as they fall into the cluster. It all sort of comes together and gets mixed. The strong mass and redshift trends that strong mass and weak redshift trends that I've just shown you then say that infall from this low-density region has to roughly be in balance, such that we see no, when low mass systems with, let's say, high stellar mass fractions fall into high mass clusters, there must be enough material with low stellar mass fraction from the field or the low density region to roughly offset that high stellar mass fraction material that's falling in from the groups. That's very interesting, and gives at least me a different picture of how this structure formation, how the mass is accumulating in clusters of galaxies. What we really need to do is to go into the simulations and try to match these trends, because that will allow us to constrain the feedback, constrain the galaxy formation models. And we've done a little bit of that, but really it's topic of a separate talk. Maybe somebody like David Barnes could come and talk on this. But basically, one could say at the level of this talk that the redshift and mass trends in the simulations don't yet really agree with the observations. So there is still more work to be done to get the feedback balanced, to be consistent with what we see, and to get the galaxy formation models to produce the stellar mass fractions varying with mass and redshift as we see in these systems. And again, as I said, once you can match the clusters, you can use the clusters as a kind of calibration data set for these simulations. Then you can use those same simulations to predict the matter power spectrum and to do cosmology. Okay, last slide then is just a summary. The cluster sample that I've shown you spans a broad redshift and mass range, the SPT cluster sample, that allows us to address these basic cluster physics questions over in a way that we couldn't do easily before. Simple selection, our sample extends to redshift of 1.75. This particular one with Chandra data is only going to redshift 1.25. We have good masses in each of these systems. 20 to 25% is what I consider good. That will improve over time as we consistently or continuously work to try to include more weak lensing and dynamical mass information. For the stellar masses and ICM masses, we see strong mass trends in stellar and ICM mass fractions. We've seen that a long time ago, 15 years ago, I think, 15 to 20 years ago, it was established in low redshift clusters. What we know now with this study is that that persists to high redshift, or to redshifts of 1.25 or so. At fixed cluster mass, the redshift trends in ICM and stellar mass are modest, suggestive of the importance of infall material from the surrounding, not just from the subclusters and low mass and groups, but also from the surrounding low density material that has basically different properties than we see in the virial regions of each of these structures. Okay, so thank you very much for your attention. Alexei.
So this notion that there are no redshift trends seems to me would depend on what definition of mass you use, because you compare those quantities at some sort of fixed mass. And that fixed mass could be M500 critical, it could be M500 mean, it could be splash band mass, it could be some number of times the general nonlinear mass scale in the universe. And you would presumably get different conclusions about redshift evolution if you use those masses. So what do you think about it?
I think
What's the proper mass to use?
What's the proper mass to use? Well, I think the masses with respect to critical are easiest to understand in terms of evolution of scaling relations. But it doesn't, you're right, that given that all these functions given that the gas mass fraction is function of radius and the stellar mass fraction is function of radius, it definitely will impact our results to make these measurements at different radii. As long as we compare apples to apples, if we're in the simulations and we're comparing M500 masses or R500 masses to the observations where we've done that, then it should go away. We should be able to look at all of these. I think the right thing to do is to study this profiles, how these properties are actually changing as a function of radius. This is a first step to sort of pull out a value at a particular magical radius motivated by the spherical collapse model. But we need to do more. This suggests we'd like to understand actually how the gas mass fraction's changing out into the infall regions, but we can't really probe beyond R500 yet, or in very many systems anyway. So it's well taken.
Could you
give us an idea of what you meant by don't precisely agree? Are they off by a factor of 2 or 10?
Well,
In what sense? Do they predict, the simulations predict any redshift dependence? Or?
Well, they do predict redshift dependence, but they have much better statistics than we have. But they're weak redshift trends in the simulations as well. So that's good. I mean, roughly, it seems like the simulations in the data are pointing in the same direction. For the mass trends, I think it's much more up in the air. It looks like we're seeing somewhat stronger mass trends. Oh, well, I'm sorry. Yeah, I don't have any of the well, right. Okay, so for baryon fraction, you can see clearly that the baryon fraction is low from our data. Maybe we should read this off the table then. Baryon fraction, you can see that it's changing as 1.29, and here's the statistical and systematic with mass. And the self-similar expectation would be something more like 1, that basically all clusters are about the same. Now, the simulations that are preferred today, I would say that the preferred simulations are showing results that are closer to 1 than to our result, and essentially with no significant uncertainties. So simulations might be showing, instead of 1.3, would show 1.1 or so. So it's easy to fix that by increasing the feedback on the ICM side, but the feedback won't necessarily affect the stellar mass fraction at all. And so it's not exactly clear to me exactly what changes need to be made to the simulations to basically steepen the mass trends. For the redshift trends, I don't think that there's any strong statistical inconsistency, but our uncertainties are still quite large. So for example, you can see, minus 0.16 plus or minus 0.16. So we still have very large uncertainties. So it's really a topic for a different talk, for someone to show. David could come in and show some scaling relations for clusters, and he could put our data on it. You get a better sense of how this works. Sorry.
So I have one question. Are there any plans to extend these measurements to larger samples where you can actually use weak lensing maps and get the mass within R200?
Yeah, so we would like to increase the sample. As you know, there are, you've analyzed 55 or so XMM observed systems. There's no reason they can't be included, and that increases our data set by a factor of 1.5. There are ongoing Chandra and XMM proposals to try to increase the number of systems studied. As regarding the weak lensing constraints, I think that maybe is a little, it's less promising than it might sound, because what we do, by using these baryonic mass proxies like the SC signal to noise or MICM from the X-ray, we're able to estimate on a single cluster basis the masses quite accurately at the 20% level. And typically with a weak lensing mass constraint, except for the most massive clusters, you simply can't approach that. And so by combining the weak lensing information, which is very weak, on each of these systems we can calibrate the overall mass scale of the scaling relations, and then at the same time, by using the ICM-based mass proxies, we can get precise measures on single clusters. So we kind of get the best of both worlds rather than doing individual cluster by cluster weak lensing measurements and ending up with very uncertain results on a single cluster basis.
If there are no other questions, then let's thank Joe again.
Well, I guess I was too imprecise. Well, I showed the tables. I thought that the tables would help emphasize that there are real measurements and measurement uncertainties.
Actually, how are you?
Sorry, I didn't respond to your email. I thought the Monday lunch is
Oh,
a
yeah.
separate thing from the Wednesday.
Yeah,
lunch
you
or
missed the
something.
great lunch.
Oh yeah, but we had a dinner together. So.
Okay. That's even better.
Yeah.
All right.
So I'll stop. Well, if I don't see you, I don't know if you're around this afternoon.
I will be.
Oh, okay. Then I'll stop in and say bye. Thanks very much.
No, thank you.
Yeah, thanks for the opportunity to talk.
So it looks like the US, if I understand correctly, the Fermi system, if I remember correctly, in all time, we expect some of the counter arguments about the excess data in the was Fermi did a lot of research with they should have seen
Modest number of, sorry, very interesting. Modest number of
your
clusters
argument
to
is
go
the
up.
position information was
Yeah,
not
if you really do it well.
so that the search wouldn't be effective enough, is it?
I think that's my, I'm not a deep understanding about Fermi, but
So I had to run out on you. Yesterday I had a building inspector come to my house.
Do you see that? Oh, is it right here?